Hello everyone, my name is Quenzel and together with my colleagues at the University of Bonn, we investigated in this paper gradient-based dissimilarity measures for visual odometry and stereo matching. If we want to estimate the scene structure from these two images of the Middlebury stereo benchmark, we need to establish correspondences. But which of the three colored patches is the correct one? Obviously the green patch is most similar, so how can we define this measure of similarity? The most common used direct measure assumes photometric consistency, meaning the difference between corresponding patches is close to zero. In reality, this assumption is constantly violated due to camera properties, viewpoint and illumination changes. We added for demonstration purposes a vignetting and slightly adjusted the overall brightness on an image from the ICRA living room dataset. This leads to unreliable depth estimates and inaccurate tracked movement, which degrades overall map quality in robotic applications. Our gradient-based similarity measure allows us to obtain more accurate disparity maps and increases the accuracy in direct image alignment for tracking without the necessity for laborious compensation. The key insight is that gradient location and orientation are much more resilient to appearance changes. We express the gradient orientation by its relation to the vector dot product. Standard vector normalization would amplify noise, as such we base our work on the normalized gradient field by Läbe and Modesitsky. We regularize the image gradient by the mean squared gradient magnitude. Simply using the dot product on the normalized gradient field is insufficient, since it would draw weak gradient regions to match with strong gradients, thus skewing, for example, depth estimates. Hence, we combine the dot product with a magnitude-dependent scaling term. Scaling with the maximum of the squared gradient norms ensures that gradients with similar magnitude and orientation will obtain a low score during minimization. If we now look back at our disparity estimation, we directly see a strong improvement over the classical photometric consistency. As such, we applied our gradient-based measure to disparity and depth estimation as well as visual odometry. For disparity estimation, we integrated our and other gradient-based measures like sum of absolute differences, or short SAD, absolute difference of gradient magnitude, short GradMag, and the norm of the gradient's difference, abbreviated as GradNorm, in Mesh Stereo and OpenCV's stereo block matching. We evaluated both algorithms on the Kitty Stereo 2015 and Middlebury Stereo 2014 benchmark and report the mean disparity error as well as the percentage of pixels with a disparity error larger than 1, 2 and 4 pixels. For Mesh Stereo, the difference between the measures is minimal, since block match disparities are used as the initializations. We obtain with our measure, especially for stereo block matching, more precise disparity maps with less dispersed erroneous measurements. We observe similar results on the Middlebury Stereo benchmark with stronger improvements for both methods with our measure. Here, again we can see less spurious incorrect measurements, for example around edges and in occluded areas. We further modified direct sparse odometry to estimate the scene depth with our gradient measure while tracking remains photometric based. On the UROC dataset, we found improvements in map quality as well as trajectory accuracy. The original approach duplicates the same obstacles seen at different times in different positions. In contrast, our resulting map is sparser, but more accurate and does not exhibit the same inaccuracies. Furthermore, we extended the optical flow front end of the visual inertial odometry framework basalt with our measure. As a result, the estimated trajectory followed the ground truth more closely. In conclusion, we presented a new robust gradient-based dissimilarity measure which combines gradient orientation and magnitude. We integrated our metric into disparity estimation as well as visual odometry systems and show clear benefits for typical disparity and direct image registration tasks. Our experimental evaluation indicates that our metric leads to more robust and more accurate estimates of the scene depth as well as camera trajectory. Thank you for watching. For more information, we would like to refer you to our paper.